When you are factoring, there are some polynomials that follow the same kind of pattern over and over again. So if you can learn to recognize that pattern, then you can take sort of factoring shortcuts. We call them special cases. So the first special case that I'm going to talk about is the difference of squares. All right. If you recognize this pattern, then you can factor these polynomials very quickly. Difference of squares is structured like this. This first term has to be a perfect square. And the second term has to be a perfect square. I don't know why I'm not writing the word square. Let's write it. Perfect square, perfect square. It only works if they are both perfect squares. And then the middle sign must be subtraction. That's the difference part. If you have an addition sign in the middle, then it is not going to follow this pattern, and this trick will not work. So this trick only works if you have the difference of squares, subtracting two perfect squares. All right. When you break these up, what happens is this. You have the square root of the first term, so 4x squared breaks up into 2x times 2x. The square root of the second term, so 81 is 9 and 9. In order to get this minus sign, you have to have a plus and a minus. All right, this is what we call a conjugate pair. All right, something plus a number, something minus a number. So 2x plus 9, 2x minus 9 is our conjugate pair. And in Algebra 2, we talked about these a lot. We like them because when I add up this outside term and this inside term, negative 18x and positive 18x always add to 0. So if you multiply two conjugate pairs, you're going to get 0 as a middle term. And you'll note that in this polynomial here, there is no middle term. So if you have a difference of squares, it's always going to factor into a conjugate pair. So the final factored form of this is 2x plus 9, 2x minus 9, and you can always double check by redistributing those. All right, this one looks fancier because, you know, it is, but taking the square root of a fraction, all right, if I'm looking for the square root of the first term and the square root of the second term, square root of the fraction is just square root of the top over the square root of the bottom. So the square root of 25 is 5, and square root of 9 is 3. Square root of x squared is x. So the first term of my conjugate pair is going to be 5/3 x. The second term is going to be the square root of the second term here. So the square root of 49 is 7. Square root of 64 is 8. So my second term in both factors is going to be 7/8. And then one is plus and one is minus. So my conjugate pair here is 5/3 x plus 7/8 and 5/3 x minus 7/8. Now, if you want to get really fun, you can look at this where there's some binomials in here. So this is a perfect square because x minus 5 is being squared, and 4x plus 2 is being squared, and there's a minus sign in there. So the square root of x minus 5 squared is x minus 5. I'm going to use my little extra parentheses there. All right, so that's the first part of each factor, is the square root of the first term, x minus 5. The second part of each factor is the square root of the second part. So the square root of 4x plus 2 squared is 4x plus 2. 4x plus 2. All right, and then this is a minus sign right here, so we have a conjugate pair. One side has to be plus, the other side has to be minus. Now this looks like a mess, but we can clean it up pretty quick. So we're going to combine like terms in the first factor, and then we're going to combine like terms in the second factor. First factor, I get x plus 4x, which is 5x. Negative 5 plus 2 is negative 3. So that's what that first factor cleans up into. And then the second one is x minus 4x, which is negative 3x. And negative 5 minus 2 is negative 7. So your final cleaned up form for this is not a conjugate pair anymore, but we use the conjugate pair to help us get there.